As you have already guessed, our first speaker of the morning is Dr. Sandra Laursen. Dr. Laursen earned a PhD in chemistry from the University of California at Berkeley. In the year 2000, she joined Ethnography and Evaluation Research, or E&ER, an independent research unit at the University of Colorado at Boulder. She has been co-director of E&ER since 2007. As co-director, she leads studies in research and evaluation that focus on education and career paths in science, engineering, mathematics, and technology, the famously named STEM fields. Her research interests include the underrepresentation of women and people of color in the sciences, professional socialization and career development of scientists, and the professional development of teachers. She is also interested in inquiry-based science teaching and learning and the challenges of improving science education in and out of the classroom and across organizations. As a research associate at the Cooperative Institute for Research in Environmental Sciences, she has collaborated with scientists and K-12 teachers to communicate science effectively to students and the public. She has developed inquiry-based teaching materials and led professional development workshops and courses for educators and scientists on a wide range of topics in earth and physical science and inquiry-based teaching and learning. Dr. Laursen has taught chemistry at Kalamazoo College in Michigan and conducted atmospheric science research at the National Oceanic and Atmospheric Administration's laboratories in Boulder. She has published chemistry curriculum manuals as well as journal articles in chemistry, education, gender studies, and the Journal of Irreproducible Results. In addition, she has co-directed a documentary film and recorded a CD with Resonance Women's Chorus. She is a faculty associate at CU's Center for the American West, and as you already have learned, she is a spelling bee fanatic. We are grateful that she has made space, not once, but twice in her busy life to speak to us at this conference. She will do so now on the topic, What Has Allie Learned? Outcomes for Students and Teachers of IBL Mathematics Courses. Dr. Sandra Laursen.
Thanks. Thank you, Lee. Good morning. Get my machine to wake up here. It's a vacation picture. It might be how IBL courses feel sometimes. All right, I thought about this talk a little bit in relationship to Stan Yoshinobu's talk. We've been chatting a bit about what he was going to say and what I was going to say. And so I sort of, slightly tongue-in-cheek, called it What Has Allie Learned? Trying to link up to Stan's very powerful stories from Thursday. And really it needs to be called What Have the Allies Learned, and the Daniels and all the others, because this is not so much this morning about the individual stories that we notice and cherish in our courses, but more of a broad picture kind of look at what students are getting out of IBL mathematics experiences in college, and how those play out from a variety of different points of view. So we have multiple kinds of evidence. And again, I want to acknowledge all the folks who worked on this. We've had a good-sized team. Our research unit is small, and just about everybody there has chipped in at various points in time. Maria-Lisa Hotze has did a lot of the data gathering work and has been the chief analyst of the student survey data as well as the test data. Marina Kogan has done the work on student academic records, the grades and course taking patterns. Ann Barry Hunter worked on the student interview data, and Tim Weston has been our statistician in chief for some of the fancier modeling efforts. So I want to thank everybody for their hard work and quick work, really. We just finished data gathering less than a year ago, and this is a lot of work to get through in that time frame. And I also want to thank the Educational Advancement Foundation for its support of this work, and to all the campuses and students and teachers who participated. Obviously, these are studies of people and people's work and people's learning, and without the people cooperating, we get nowhere. So let me remind you, I've spoken about this study at this meeting several times before, so this is probably a slide that's starting to look as familiar to you as it does to me. And so this is a large, what we call mixed method study, meaning lots of tactics used at the same time. We're looking at IBL as implemented in 4 university research departments that have these IBL centers that you'll hear about later this morning. And our research questions focused on the student outcomes of these courses, including mathematics learning and thinking, but also the affective and social outcomes that are important. How do students change as people, as in their emotional and maturation processes? How do these outcomes vary for different student groups? Not only comparing IBL and non-IBL courses, but also looking at differences by gender, by the type of course for math majors or pre-service teachers, by their previous achievement in mathematics. And finally, we're very interested in the processes by which these outcomes arise, and that includes the roles of students, instructors, TAs, the classroom materials, the classroom practices. I won't have time to talk about all of these things today, but I want you to make you aware that we know about these things. We're also very interested in the outcomes for the teachers themselves. How do faculty and grad students and postdocs who participate in these courses as instructors develop as teachers? What happens to them later on? Do they keep doing it or not? Just quickly, we think of this as sort of a checkerboard design. We look at a variety of different outcomes there across the top, the kinds of things I just mentioned. We have multiple tactics. We use surveys, we use interviews, tests. We do a lot of classroom observation. We look at academic records. And I want to just point out, so that we're clear from the start, we separate the students into 2 groups depending on the kind of course they take. So really we're separating courses, not labeling students individually. And we look at what we call math track courses, meaning courses that are either for students in the mathematics major or minor, or for students in STEM fields that would be taking a lot of math, or beginning courses for students who you hope to suck into your major. So those are the math track group, and we separate those from courses that are very specifically targeted at pre-service K-12 teachers, so things like mathematics for elementary teaching. And the reasons for separating those, I think, will become clear. Where possible, we compared IBL and non-IBL courses. That wasn't always possible. There was not always a non-IBL version of the same course. And what you see from the summary, I won't go through the numbers, but it's a big pile of data, okay? So this is a large study, and we've tried to be quite comprehensive in our data gathering efforts. Let me also remind you that this is a study of the real world. People are interesting and messy creatures. They do things that they want to do and not necessarily what we want them to do. So it's more like bird watching than it is like doing laboratory chemistry. In the sense that we have a whole variety of things out there, the wildlife. Your students and you are the wildlife that we're studying. And there are lots of different courses. There are 4 different departments. Each department has its own culture and style, not only for doing mathematics, but also for teaching mathematics and for teaching IBL. They've implemented things a little differently. There are lots of different courses. There are lots of different mathematical topics. And so all those things introduce a rich and interesting variation into the study. It's also kind of a, from the point of view of a researcher, it can be a little, it's rich and interesting, but it's also kind of a pain because it means we have to be very clear, what is the thing that we're studying, right? If we call this IBL, we have to characterize what IBL is. So it's kind of like characterizing an ecosystem. What's in the ecosystem? How do the birds and the creatures and the plants interact? Okay, so that variety is lending strength to the study, but I just want you to be clear that this underlying variety also complicates what we have to say. For that reason, I also think it adds a great deal of power to what we find. This is not an idealized laboratory setting. This is what it looks like in the real world. And if we can see a strong signal that IBL is doing something with all that variation, that tells us it's a strong signal indeed. So this is what reform looks like in practice, not in theory. All right, so let me start by saying a little bit about what is inquiry-based learning. That's an important thing to set up. If we're going to compare students who do and don't experience this approach, we need to know what is the approach. Are they swimming or taking a boat to the final destination? What we see, let me start by telling you a little bit from what instructors say These are quotations from the instructor interviews. What instructors say this is about is getting students to engage in the material, getting them to figure things out for themselves because they believe that helps students understand them deeply. They see that it's important for students to explain their ideas to someone else, and that in that process making it their own. If you have to talk it out, you have to understand it, or you find what you do and don't understand in that process. They want students to learn how to learn, whether it's a particular mathematical concept or perhaps more broadly, how to learn new and hard things. And they want students to develop confidence in their answers. They want students to see that they can be mathematicians and can discover and figure out if something is right, whether or not the teacher validates that answer. And that's a really powerful process of owning those ideas and discovering that math is done by people. What students tell us about, from their point of view, their experience emphasizes what I've called the twin pillars: deep engagement with the mathematics, collaborating with others. And I've put up some student quotes here that help show this interdependence of these two. Students say, I do have to work harder, but I feel like when I've finished a proof, I've actually accomplished something. So that student is referring there to the fact that the task is meaningful, right? The task is worth doing, and when I get done, I feel a sense of accomplishment. It's not the same as spitting out 20 repetitions of basically the same problem. They say once you spend time alone with it, meaning the material, then talking to other people really helps solidify it, right? So there's a linkage between the individual engagement and the collaborative practice of talking to others, working out your ideas. You really get it after you've done that. You can't just write the proof up on the board and expect everybody to get it. You really need to explain it. Explaining it further helps me get it too. Again, a link between their understanding and work on the mathematics and the process of communicating it to others, enforcing that link. We have to work in the group, says one student. We can't do this alone. So that's a reference to the fact that the tasks are hard. They're challenging tasks. As the first quote says, they're meaningful tasks, but they're also difficult enough that it requires the group effort. So again, a linkage between the work and the way of doing the work. What we see then also that students are telling us is out of that process of engaging deeply with the math on their own and working with others to sort it out and refine it and improve it, there are lots of very positive side effects, not only learning the mathematics, but learning how to persist, learning that their own effort is worth doing, it pays off, getting a sense of responsibility to others. I have to be prepared for class because my group is going to need me. My class is going to need me to be ready to talk about this material. They develop communication skills that they see as widely applicable beyond just talking about math. They develop confidence, and they really, really find it very powerful to see the other ways of solving the problem that their fellow classmates have developed. Some of them are just amazed. You know, that person solved it a completely different way than I did. I had no idea that you could even do it that way. And that's very powerful for them to see that mathematics has multiple ways of getting to the right answer. All right, so those are quotations for people describing the practices. We also went into classrooms and observed what was happening. So the campuses themselves identified which classes were IBL or not IBL. We also went in and looked, right? Trust but verify, as I said. So these are averages. These are pie charts just showing the different instructional practices on average in the classrooms. So what you see is that the warm colors include student-centered activities, students presenting at the board, students working in small structured groups on organized tasks, students discussing as a whole class. Then the cool colors are the more instructor-centered activity. Lecture, which we define as pre-prepared material you plan to present. Explanation, which are more spontaneous talking in response to a question or an issue that comes up. And other sort of includes, handing back homework and what's the test and do I have to know number 42, that kind of stuff. IBL courses we also observed differ in other ways. So we tracked simple things like how often the class activity changed gears. Much more frequently in IBL courses. Things change up. There's more students, if nothing else, you wake them back up when you change what's going on. Students take the lead more often. They are more often in charge of what's going on in class. in the moment. They ask more questions, and more students ask questions, right? So we just counted who asked questions and how many. We also had our classroom observers rate what was going on in class, just the frequency of how often, relatively speaking, do students interact with each other to get help? How often do they ask questions of each other? How often do they ask questions of the instructor? How often does the instructor pose a question? You know, things like that that were just behaviors indicating interactions and responsibility for the course direction. And what you see there on the bottom part of the table is that if we sort of group the like activities together, there's really, again, quite significant differences between the nature of interactions going on, that students hold joint responsibility with the instructors for the course direction. And I want to point out that the bottom line is not different, right? And that's the case where the instructors, those are instructor behaviors, the instructor setting a positive atmosphere. And I think it's important to notice that the difference here is not significant. In other words, the instructors in the non-IBL classes also cared about their students. They wanted class to be a good experience. So the difference is not their intent or their goodwill or their friendliness. It's that they chose different instructional activities, right? They're having students meet the math in different ways. So it's not about, you know, this guy is just nicer and that's why this works. It's about what is going on in class. All right, this is a graph that shows you that variety I mentioned, right? So I showed you the pie charts, which are averages, and what you see is that the average is strongly different. Here's a measure of the variation. So these are bar charts in those same color schemes for the student-centered activities that are going on in classes. And they're presented there for 3 different campuses and then comparing those to the non-IBL courses. And what you see, again, it's really easy to tell the difference, right, in general. However, there are some individual courses labeled IBL which don't look as different from the non-IBL. So there is variation within those broad differences. Okay? And you also see that there's different, what I mentioned that were different campus cultures. You can see that in this figure, right? You can see that some of the campuses had quite a lot of structured small group work in class. In some places, the 3rd campus over there, that turns into whole class discussion. In other cases, students are presenting more often. In this case, we have a more presentation-focused approach, and sometimes it bursts into discussion frequently and sometimes less frequently, right? So there's variation from campus to campus, but on the whole, very significant differences in the practices, okay? And you might be saying, well, yeah, I knew all that. I mean, that's why we're here. But I want to make the point that we can confirm these things are different. And if we can do that, then it's worth going ahead and studying what students do or don't get out of this, right? If we saw no difference in the average classroom practice, we would stop. We wouldn't go on to study student outcomes. So, again, the way we would characterize from our observations, from the interviews, from the survey data, which also talks about the classroom activities, these are the important differences or the important characterizations, let's say, a description of what IBL is about. Students are solving challenging problems, alone or in groups, often both, sharing their solutions, analyzing and refining those. Class time is used for those student-centered activities. Students take a significant leadership role. Things change gears. The course is driven by a sequence of problems or proofs. We have a lot of discussion at this meeting about what should that sequence be. Are there sequences for the course I want to teach? So you know that's important, and that's certainly a commonality that we see across the courses. The pace of the course is set by students' progress through that sequence. The course goals tend to have more emphasis on thinking skills and communication than their comparative courses. Content coverage. Content is important, but it's less central in the list of course goals that instructors supply. And therefore, the instructor's role is significantly different, again, as we have much conversation at this meeting about. The instructor is the guide on the side, not the sage on the stage. He or she is managing, monitoring, summarizing, cheerleading, encouraging, all these things which are facilitating the work of the course rather than delivering the material. All right, so now that we've established that there is a difference between swimming or taking the boat, we want to look at what that difference leads to in terms of student outcomes. So I want to just talk, we have lots and lots of data, and I can't talk about it all today, but I want to just talk with you about 3 claims that we're making, and I want to show you some of the evidence for each of the claims. I can't show it all to you, but I want to give you a flavor of the types of evidence we have for each of these claims. First of all, that IBL instruction has positive outcomes for students, especially for women and for students with lower levels of initial mathematics achievement. So let's take those one at a time. Let me start by just saying that two of the kinds of data that I'll show you, well, the bar graphs you're going to see in a moment are mostly from our general measures of outcomes, and those tend to focus on the survey data that we have about students' learning gains. They're reporting on their own learning gains, responding to questions, how much did you learn? This is on the SALG-M questionnaire that several people in the room have used, I know, and you're also welcome to use it, as well as affective gains. Affective meaning confidence, positive attitude, interest, things like that, emotional or personal gains. And the reason we use this survey is because it's something we can give to everyone. It doesn't matter if they're taking number theory or analysis or math for elementary teachers, everyone can answer the same questions. So it's our broadest kind of measure, right? Once we start trying to do things like give tests, we shrink the sample size a great deal because now we can only give a test to the students who are taking the same kind of course. And even from campus to campus, you know that analysis on this campus doesn't play the same role in the curriculum as it does in another place, so that even two analysis courses are not always comparable. So the survey, the Learning Gain Survey, is our strongest, broadest measure that we can use. And these are the sample sizes, hundreds of students in each of the three groups that I'll talk about. The other thing we looked at carefully, and then I'll show you graphs of in a moment, are grades. Grades and course taking patterns, number of courses taken. And the way we do that is we say, okay, here's a target course, a particular IBL section of analysis, let's say. And then who are the students who took that course? Who are the students who took the comparable non-IBL course? We look at what happened to them before they took that course. So we're looking to check if they're different already coming into the course. And then we look at what happens to them afterwards, right? So we're comparing particular courses and sets of students. And we look at several different clumps of grades, you know, required grades, or courses, grades in required courses, elective courses, and so on. Okay, and again, hundreds of students in that data set. So it gives us pretty good statistical power. I'm going to be showing you data from just one particular course. We've done that analysis for some others, but we can't bundle them together because they're different courses. All right, so here's some data from, starting with the first claim about IBL is good for students in general. These are showing you the cognitive gains, meaning the intellectual things, mathematical concepts, gains in mathematical thinking, gains in applying mathematics to other types of problems, and gains in comfort in teaching others, right? So that's sort of an indicator of, I think I know this well enough to tell you about it. Well, maybe not you, they're peers anyway, they know it well enough. So what you see here are statistically significant differences between the IBL math track students and the non-IBL math track students. The differences tend to also be significant for the pre-service teachers. And what you see is that really across all the types of gains, IBL students outperform or report higher learning gains than the non-IBL students in the comparable math track classes. For the pre-service teachers, we don't have a comparison group. All the courses we could study were already IBL. So we don't have a non-IBL pre-service teacher set of courses to compare. But we can say that it's clearly they're a different group, right? They have different starting points in terms of their interest and use of mathematics. And so their learning gains do look different. They are lower in some of the conceptual things. They are higher in application and teaching, two areas where we might particularly hope that our pre-service teachers make good gains. The affective gains, here we're looking at confidence, positive attitude, and persistence. Again, IBL students report higher learning gains than non-IBL students in the math track group. And again, the pre-service teachers have sort of a different pattern. So those are just some examples of some of the things. Let me summarize what other lines of evidence we have about this. So the self-reported learning gains I've just shown you. Interviews very strongly corroborate the kinds of gains that students report. They talk a lot about, you know, for instance, with concepts, they talk about really deep learning of that. I'm not going to forget that, right? Like paracompact or whatever it was, right? They remember it. Because they know it well. They've studied it deeply. They know it inside and out. So they say the same things in the interviews as they report strongly on the surveys. They talk about, well, we also have data where we look at their attitudes both pre and post, right? So learning you can only look at afterwards. You can't say, what did you learn at the beginning of a course? But you can ask about things like confidence and attitude before and after. It's a little tricky because the yardstick can move in between, right? Sometimes experiences actually show us how little we know, or that perhaps our confidence was overstated once we find out what there is to learn. But when we do look at those attitudes pre and post, for instance, interest in mathematics, both as a major and as a personal interest, something I talk to my friends about or read about in the newspaper, we see small gains for the IBL students, we see declines for the non-IBL students, right? So we're actually doing some harm to the attitudes of students in non-IBL courses on average. And remember, these are averages. Tests, the tests we gave to students, it was a test of their ability to evaluate mathematical arguments, so we sort of targeted that at some of the courses that are introduction to proof kind of courses, functioning a little differently in different places. But those tests show that IBL students, there's no overall difference in the score, but they do apply more sophisticated criteria in evaluating arguments. I will say that because we could not give that test in class, the sample there was volunteers, and volunteers tend to be good math students, right? Anybody who thinks it's fun to come take a math test, even for $25, is fairly confident of their mathematical skills. So, and we're not allowed to offer enough money that would actually induce the lower students. There are human subjects rules about that. So there are limitations to that sample, and it's very strong students. But I think it's encouraging that we can see the difference in their reasoning, right, from a fairly sophisticated kind of analysis that they're doing of these arguments. In later courses, IBL students do as well or better grade-wise, and they take as many or more courses, depending on which set of courses you look at. Gender is another particularly interesting area. So once you start breaking down these student groups, you see some differences that I think are even more interesting than the overall differences, and perhaps even more worth thinking about where they arise from. When we break students out into men or women, so we've got men in blue, the darker color is the IBL shade, the lighter color is the non-IBL shade, the women are in red. Again, these are the learning gains surveys, cognitive gains that students report. What you see is that men and women in IBL courses report equal gains, right? Both report higher gains than their non-IBL peers. But when you look at the difference between men and women, you see that women report, in the non-IBL courses, report much lower gains, really quite statistically significantly different gains across all the types of gains that we see, right? So while IBL experiences are equitable for students, their experiences in the comparative courses are not. The same is true when you look at the affective gains. Women's confidence, women report lower confidence coming out of a non-IBL course than they do out of an IBL course, much lower than their male peers, right? So there's a big gender gap there. If you look at grades downstream, these are sort of 6 different collections. This is the current semester grade. Women actually do better in the current semester and the target course itself. But downstream, the gains are less distinct. They're not statistically significant. But you can see a pattern there, right? Women's grades are a little better if they took an IBL course than if they took a non-IBL course. This is not the grade in that course. It's the grades later on when everybody's taking the same courses. So the IBL students are doing a little better than their peers. But again, the women are not fully catching up to the men on those measures, right? So in other words, the IBL course experience itself seems to level the playing field, and everybody can succeed. Downstream, that effect is not sustained, right? They're back in the same courses that were so problematic on the previous graph. So it's a good thing for women. It doesn't solve the problems that may be going on in courses elsewhere. All right, so to summarize what we see, again, there's other kinds of evidence that I can't show you today. The self-reported learning gains are highest, are lowest for non-IBL math track women, whereas they're equal between men and women who are in the IBL course. IBL women also write in, another kind of analysis we do is we look at the written comments on the surveys and just look at, we can count them and categorize them. The women in the IBL course write in a lot more gains than other people. They have a lot to say about this learning experience. In the attitudinal measures that I mentioned, the pre-post, again, women's confidence and motivation goes up after an IBL course. It goes down, the confidence, collaborative work, and use of effective learning strategies goes down for the non-IBL women. We're doing some damage to their confidence and their learning approaches. In the later courses, as I said, those gains are somewhat sustained, but not completely. So we've thought about this a little bit. We're starting to look at the research literature. I think actually so far the best insight I've had is from this XKCD cartoon, which is that we still do label students by gender in courses like mathematics and science. That phenomenon has been described for a long time in the literature, and there's really no evidence that it's entirely gone away. What has gone away is the differences in women's initial preparation. Your women students are coming into your universities just as well prepared in mathematics, or some evidence suggests better than the men. So it's not a deficit of background at this point. Women are taking the AP calculus test in similar numbers, or AP courses anyway, in similar numbers. So this is not an issue of the women having less preparation, but they are still, I think, they feel noticed, they feel self-conscious, I think, in the courses, and there's research evidence to suggest that as we've been looking back. So the chilly climate stuff that was done in the 70s and 80s, we don't have particular reason to think that's entirely gone away. The dearth of women peers and role models has been proposed as an explanation, and I think that has not entirely gone away. There's a lot of recent work on stereotype threat, which is exactly what this cartoon is about, right? That if you feel like you're representing your gender, you're more self-conscious and less likely to do well on a test. From the interview data, we interviewed IBL students. We did not interview non-IBL students. In retrospect, I kind of wish we had, but we don't get reports of gender difference. So again, that's part of the reason for our claim that students are having very equal classroom experiences. I think it's also significant that in an IBL classroom, everybody's work is visible, right? Everybody makes mistakes. Many people at this meeting have talked about the importance of seeing people make mistakes and realizing that math just doesn't come right out of your head, you work at it. That may be more important for women, to see that their male classmates don't really understand this any better than they do, and that they are working just as hard. There's certainly evidence that, well, you know this. You've taught 18-year-old men, and you know they can be pretty cocky creatures. So they are, if the women believe that, they may be underestimating their performance and thinking that the men are really nailing this more easily than they are, and therefore seeing others work, seeing that we're all working hard at this, that we all have insights from time to time, and we all screw up from time to time, may be particularly important. All that's kind of speculative, but I think there's interesting things to explore there. All right, now when we talk about the achievement groups, here we've sorted students into high, medium, and low grade points previous to the IBL course, right? So students are reporting their GPA coming in. We have to sort them slightly differently depending on the study. Students don't know their mathematics GPA, so we can ask them their general GPA. For the academic record study, we can actually count their math courses and calculate a GPA. So we have slightly different criteria for sorting high, medium, and low depending on the study. But what you see here is that the students with the lower grades coming in report in some areas much higher gains than the students who start as higher achieving. That pattern, look at the blue bars are the non-IBL students, and you see a stair step, right? Students who start with better performance end up report higher gains, right? The rich get richer in a non-IBL course, right? The stair steps always go up. Whereas in the IBL course, the stair steps do not always go up. And in a couple cases, mathematical concepts and application, the lowest performing students report higher gains than their more well-qualified peers, right? So that's an interesting pattern that suggests that IBL is giving a particular boost to those lower achieving students. So when we saw that, we looked for that same pattern in the grade data. And what I'm plotting here is the improvement from before to after, because here we're actually looking at transcripts. We can actually calculate their GPAs for, again, the same set of students, low, medium, and high achievers in the IBL course, low, medium, and high achievers who have taken the non-IBL course. And what you see is a really interesting pattern, right? Almost everybody does worse in later courses than they did in earlier courses. Well, why is that? It gets harder, right? The upper levels of your curriculum are more difficult than the beginning levels. These students are good math students, but it gets harder, and so their grades tend to go down, right? The standards are going up. But that's not true. There's a very striking pattern that the low-achieving students who had an IBL students do better from 0.4 to even 1 grade point unit in later courses than they had done previously, right? And the important thing here is that the picket fence goes up, right? That light orange bar. It's going up consistently across their grades the next semester, their grades for all the required courses they take later on, elective courses, and so on. And if they take another IBL course, they really soar. Yeah?
Is there any attrition of students, the weaker students not taking as many of the harder courses later?
We don't see very big differences in the number of courses taken. They do not take more courses. It does not inspire them to go on. But they don't seem to take less. So the lower achieving students are taking what they need to get through. And that's a limitation of this kind of measure, right? Students are wise creatures. They tend to do what they need to do. So we don't see a difference in the numbers of courses that they take. We don't have a way of measuring attrition, the immediate attrition. We don't know how many drop the first week, and if there's a pattern in who drops the first week. But we don't see differences in the course-taking patterns downstream for those students. So it's a good question, thanks. All right, so does this make sense, the graph? Right? Students are doing better. And I want to point out that, grade data is noisy, right? We spread students out in grades on purpose, right? We assign a range of grades. So there's these standard deviations are big, but we're talking here about, 0.5 to 1 standard deviation effect on these low achieving students. That's a big effect in education research. All right, so to summarize, again, we have some other streams of data that sort of point in the same direction as this. The self-reported learning gains are highest for the low achievers. I didn't show you the data for the pre-service teachers, but that effect is even more pronounced for them, right? So for the pre-service group, the lowest achieving students make the greatest gains. These gains are higher, not only the low versus the medium group, but also the low IBL group versus the low non-IBL group. The higher achieving students, we don't see a difference. There's no harm done to the good students, but the lowest students seem to get a boost. On the test, we gave a pre-post test to the pre-service teachers. I mentioned that the other day. And again, we see that the low achievers, the people who had the lowest score on the pre-test, make the biggest gains to the post-test. And again, that's not because the best students are maxing out the score. It's a fairly challenging test. There's room for improvement for everybody. But those students are really making significant gains. In the later courses, the IBL low achievers' grades improve. That's the picket fence graph you saw. Later, everybody else's grades go down a little bit, right? Not a huge amount. Again, these are noisy data with lots of spread in them. And everybody else's pattern is the same, right? It gets harder, whereas even though it's getting harder, the low achievers do better. We have some evidence that the high achievers do take more courses. So an IBL experience seems to prompt, at least at a small level, them to take more courses. Their low achieving peers do not. It's hard work, right? You know that. Okay, so just to sum up then, I've given you a sampling of the evidence that we have for the student outcomes. And again, XKCD has a lot of wisdom, right? How do I know that these things, I keep grouping things into IBL and not IBL, but I want to also show you why we think IBL, that label, is an important thing, right? I could randomly group students by lots of things. How do I know that these differences are in fact due to the IBL nature of the course? Now this is a complicated graph, but I want you to do a little inquiry here with me this morning. So what we've done here is correlated the course average for student learning gains, right? So those survey data averaged for each section separately. And I haven't labeled the sections IBL or non-IBL, but instead I've plotted them against the class time spent on those student-centered activities, right? Those orange and pink slices of the pie, or the slices on the bar graph that you saw earlier. So I'm looking here not at the IBL label, but at what is actually going on in class, right? In general, that relates to the IBL label, but this is a more precise way of doing it. It takes into account the fact that some non-IBL instructors do some fairly student-centered things, and some there's variation across those practices. So I'm plotting the course average and gains versus the student-centered activities, and then I've shown you fits to the orange and the green data sets. And what you see, the orange data set is the math track students. Two kinds of gains there, the mathematical thinking and the affective gains, the confidence and persistence things bundled together. And what you see is the slope goes up, right? So in other words, the more student-centered activities going on in class, the higher the student gains report on average. And this is a really simple-minded fit, right? We're forcing this to be linear. It's probably not linear. In fact, if you kind of look at those points, they go up and then they kind of level out, which makes much more theoretical sense, right? You shouldn't keep getting better the more student-centered stuff you do. Instructors have a role, right? And so at some point, after you get to a fairly high level of student activity, it should kind of level out. So we're forcing it to be linear, which is a simple-minded approach. We're collapsing all the students' answers into one data point, even though we know there's a spread. And yet we still see this nice upward linear trend. The other thing you see, the orange data points are for the math track students, and the green data points are the pre-service teachers. And what do you notice there? They both go up, right? So again, doing more student-centered work in class is having a positive effect. But the pre-service teachers, things start lower, right? Again, they have different uses for mathematics. They have different attitudes about mathematics. They're harder to please. Your math track students are, they're happy whatever you do. They like math, right? Whereas the pre-service teachers, they're the canaries in the coal mine, right? They're the people that we need to work harder to make this work for them. They're more likely to have had less successful experiences with mathematics in the past, right? So the fact that we get a positive slope for them means IBL works for them too, but their starting point is different. And to get those good effects takes some significant thought and design on your part as teachers. Right? So again, as I said, this is a simple-minded way to model this data. It's not really, I don't think a linear fit is really the right way to model it, but it gives me a visual that I can sort of show you the patterns and trends in the data. We've also done some sophisticated modeling. It's called hierarchical linear modeling. It takes into account multiple kinds of effects, and it is sort of a clever way to handle the fact that students vary within a class as well as classes varying among each other, right? So this variable on the bottom is a class-level variable. It's not a student-level variable. Everybody had the same thing happen to them in class, if it came. But there's also variation among students, as we've just seen, gender, performance, and so on. When we do that hierarchical modeling, again, this variable, percent of time spent on student-centered activities, is the single best predictor of learning outcomes, right? It's a strong positive factor. Okay, so the take-home message that we draw from this is that if you change what you do in class, if you change how students meet the mathematics towards more student-active approaches, having them engage, whether that's through group work or discussion or presenting or responding to presentations, all the things you do, all the ideas you've had here at this conference that you've discussed, changing those activities from lecture to students doing stuff makes a positive difference. That's what that graph and the more sophisticated versions show. Okay, now the art of this, so you can do some good just by shifting your choice of activities. To get it to work really well, then, is what this conference is all about. It's the everyday choices and acts that you make as teachers that then refine your practice, right? So getting it just right for your students, for your setting, for your course, for your material, is then the art, right? So there's sort of two levels of this. One is making the change, and the second is refining the change, right? Just like students, in fact, right? Do the proof, then refine the proof. And the choices, the thing that should guide you in making those choices, steering the ship, if you will, towards a successful destination, the thing that should guide you then is how can I enhance those key learning processes of individual engagement with the mathematics and working with others to sort it all out and make sense of it, right? The collaboration and the engagement pieces, how you do that. And exactly how you do that, whether you choose small groups or whole class discussion, is up to you, and it's, again, the main topic of this conversation, but that should be the guiding principle in your head. That's your compass, if you will.
What does the picture on the right represent?
That represents, it doesn't usually go that badly. Someone said that there was value, someone said yesterday that there was value in exaggerating and taking the extreme cases. So the extreme cases, the ship tips, that one would be a little harder to write than some of the others. So maybe you better stick to the kayak. So just to sum up, and then I hope we have some time for questions. You've been waiting patiently for several years to find out what is X, and here's your chance to learn about X. What we think is powerful about these data are that the patterns across these multiple outcome measures, which really get at things in rather different ways, all point the same direction, right? Somebody said this to me yesterday, the vectors all go the same way. And I think that's a robust finding, right? To some extent, it's a little surprising. We don't always, we tend to have more mixed findings that we have to then puzzle and scratch our heads over. So the fact that things really all indicate the same good outcomes for students, I think is very significant, even though we have this great variety in the practices that we're studying in this naturalistic setting that we've been able to study. So this is good for students in a variety of ways. We have evidence, again, several streams of evidence that indicate that this is particularly good for women. It levels the playing field and takes out things that may be discouraging women or having them feel less successful and confident in other kinds of courses. It boosts the low-achieving students. I think part of that what is going on is they're working hard, right? This is a motivating thing. They have to be ready for class. And so to contribute, to feel like they are part of it and they are moving along with the course, they're probably working harder, but they're also motivated to work harder, and I think any method that does that for students is a good thing that you want to hang on to. There's no harm done to the men, to the high achievers, right? So we're evening things out and letting everyone be successful in the ways that do not do any damage to anybody else. The student outcomes are clearly linked to the classroom use of active learning approaches, right? And there's nuance and subtlety in exactly how you execute those and choose those for your own course. The key learning processes that we hear about and that show up again in survey data and interview data and in other places are deeply engaging with the mathematics on their own, coming together to work together to sort it out, make sense of it, own it, right? So that talking it out and listening it out, if you will, are very critical for students' learning. And so that's where you choose your practices to optimize, right? Those are your guiding principles when you go home. The executive summary has been referenced. More copies are available around. If you'd like to take home a hard copy to read on the train or the plane, you can also get a copy at our website. If you want to jot that down, you can, or you can Google us. It pops right up. I checked. And we're happy to have your comments and thoughts about what things mean and what goes on. Yes, there's holding up copies of the executive summary at various corners of the room. So please do feel free to take a copy. I'm happy to take questions if we have time. Lee?
Go ahead.
I really like your study. I think it's a great study, but I have two questions. Right. The first one.
Please stand up.
Oh, sorry. My first question, at the end you compared the percent of student active learning versus learning gains. When you say student active learning, did that differentiate between IBL and other forms? Because I think there are many kinds of active ways to engage students that
Well, the courses that were in this study were all calling what they did IBL. And as you saw from the bar graph with all the variation, that meant different things to different people. So that's why we took the IBL label off and simply looked at the sum of the whole class discussion, small group structured work, student presentation, and in a small number of courses there was computer lab kind of work, modeling and simulation. So we took all of those as our student-centered work summed up. So it was the percentage of those things added. But we don't have an indicator that says what is the nature, we didn't separate that from the sequence of problems or other things that might characterize inquiry, but all the courses in the study were doing that.
And then my second question then, I'm wondering if there might be a lurking variable specifically that most IBL instructors are fairly motivated to modify their teaching techniques. They take initiative. And I wondered if you had been able to correct for the fact that maybe some other instructors who do traditional methods just do it because, and whereas some other instructors who may not use IBL might take the initiative and go a different direction, and if you compared them to the IBL instructors.
There were a few instructors in the study, in the non-IBL group, who were fairly active. There were certainly some lecture courses that really had a fair amount of interactivity. So that was the beauty of plotting it with the student-centeredness, is that they're further over to the right on that axis. And so by taking the label off and using instead an observed, measurable variable instead of a human descriptor of that, we can include them. Their methods are included in that upward slope, right? When we look at the instructor's characteristics or qualifications themselves, we do not see patterns. While there are a few instructors in this study that are quite experienced practitioners of IBL and quite skillful at it, there were a bunch of newbies. And they made newbie mistakes, like we all do when we're new at things. And there are courses across that axis that were represented. So if you plot it out, and you look at experience levels of instructors, how long they had been doing this, how long they had been teaching altogether, you don't get any correlations. We looked at that. We also looked at gender of the instructors. We're a little bit hampered in that not a huge number of the instructors were women, but we didn't see a pattern there, right? We did not find that there was a matching of student outcomes with the instructor's gender either. So we don't see a pattern there. And a lot of these instructors were brand new to it. They were being coached and helped along by their colleagues at the institution where they were, but they were not necessarily skillful to start with. And as I mentioned on that one slide, we don't see global indicators that the IBL instructors were just more caring or more interested or more concerned. I think there probably are some personality differences in who chooses to do this. But we don't see an effect of sort of global teaching skill. We don't have any evidence for that.
I have also had two questions, but mine are non-sophisticated.
Well, let me finish just answering her comment. I think that yes, the charts are not in the executive summary. They are in the full report. I warn you before you print it. It's 204 pages. And we can certainly make the PowerPoints available after the meeting.
The website?
Sure, yeah, why not?
Okay,
Thank
you're
you.
all right now?
Pictures do speak 1,000 words, so thank you.
Mine refers to the earlier bar charts, and they're non-sophisticated questions. The first one is on the gains. I think your scale was either 0 to 5 or 1 to 5. Mm-hmm. They're all up around 3.5 or 4.5. What would have been not significant? Down around 1 or 2?
Let's see. The difference between the non-IBL, let's see if I can go back to that, maybe illustrate that point. The difference between the blue and green bars is not significant. The difference between the orange and blue is. They're not terribly different, as you can see, right? So they're close. That significance has to do with not only the size of the difference between the bars, but the scatter, right? That's represented by that average, the spread. And partly it has to do with sample sizes also. So we have more IBL students answering, therefore our average is kind of pinpointed more firmly, if you will. So the differences between the blue and the green bars are in these first two sets are not significant. They are in the second two sets. Does that help? So it's not so much where the answer is, it's the difference between the answers that matters. And these are significant, but not hugely significant. These differences tend to be on the order of 0.3, 0.4 standard deviations, which in education research we would call a medium-sized effect, right? So these are not giant effects, but they are significant.
Well, you're going to try to highlight that in later discussion, I assume,
Sure.
for people that are non-specialists.
Right.
My
Yeah, I know.
second-
It's hard. It's hard to find ways to communicate statistics when you're not familiar with
My
it.
second very quick question is, you had earlier said that this is one of the largest studies for STEM research of this type. Could you just amplify that, please?
Sure. It is, these are pretty big samples, right? Hundreds of students, 1,200 students answering these surveys, for instance. That's a good-sized sample across many courses and multiple sites. We've done a literature review that's not summarized in the summary that you have, but it is in Chapter 1 of the full report if you'd like to see that. And we've just looked at what previous work had been done on inquiry-type approaches in college mathematics. It's not a vast literature, right? There's not a huge amount out there already. Some of the data is from the calculus reform studies, or calculus reform work that some of you were involved in the 90s. And there's been other smaller studies since then of more method particular things, the emerging scholars work that Eric Hsu reported on yesterday. So there are some studies out there, and this is a big study compared to most of them. It's not a giant study, right? It's not David Bersoud's sample sizes of thousands of students, but it's a different approach. Yes, there was a question in the middle back there. Oh, go ahead. You've got the mic.
This is even less sophisticated. But I think you may have answered it on Wednesday, but I don't remember. Your pre-service teachers, does this include secondary, middle, and elementary school all lumped in one population?
This includes all the courses for which a targeted course was taught. So yes, it includes on one campus, there were two different strands. There was a mathematics for elementary teacher strand and a mathematics for secondary teaching strand. On another campus, it was sort of a mathematics for elementary and middle school is how they bundled it. But they were all targeted courses which were not counting towards the math major. Whereas in some of the other courses, number theory, geometry, analysis, and so on, there are people intending to become pre-service teachers at the high school level, but the course is open to all math majors, and we don't separate out those students from their peers. We separate by courses. So yeah, it does include some secondary courses, but they're all targeted, aiming at how do you get ready? What math do you need to know to be ready to teach? There was one back here and then here.
Yeah. So I'm a little bit surprised by your finding that the students' sophisticated thought about proof only slightly increased. In the more method classes I teach at Baylor, the intro to proof class, those students, they work so hard at the end of the semester when I teach to the next class, advanced calculus, and I have students who had a more method intro to proofs class and a non-more method intro to proofs class. My more method students need no preparation. They can walk into the class and do proofs. They can think sophisticatedly. The other students, it's like I'm starting from scratch. They're completely different. So that finding, I'm really puzzled by that. I wonder, you had a slide up that had the different percentage of activity time in each class. In my more method classes, we don't spend 45 minutes collaborating. I hope they're spending 5 or 6 hours outside of the class working hard on proving theorems. And that is a totally different type of activity. You seem to be clumping IBL all together. There was one class on the slide where you had this color bar going up with the percentage of student-centered activity time. There was one class on the side that would look like my class. It was 90% or so of this student presentation time and a little bit of instructor-directed time. And then there were these others that were more than half group work in class. Now, if I go in and I'm giving them a project they can solve in 30 or 40 minutes, that's just so different from, so this Campus L.
Yeah, right, I understand.
I mean, it's just that is so different than Campus W. So do I expect the students who have done these group projects to have the same level of sophistication when they walk out of the class as if I've been making them work 4 or 5 hours a week outside of class, alone, struggling with a problem? I would see, it's totally different. Is there any hope? I mean, I really would like to see a study of classes that look more like that Campus L. And I hope we see a huge increase.
The test data is from that campus. And it's from students who had those presentation-focused experiences.
Which was?
The test data that I mentioned, the evaluation of mathematical arguments.
Just a slight improvement in sophisticated. I mean, I wouldn't convince a dean with slight improvement.
Sure, I understand your point. Let me respond, which is, as I said, those were self-selected students. We did not have any instructors agree to give a test in class. I think that means, well, I know that means we asked students about their grades and their prior math experience. The students who volunteered to take the test for us outside of class for a small monetary compensation and whatever fun they had doing it, were strong students. They were confident students. They had a lot of math background. We did not get C students volunteering to take this test. I think that's where the test would be more sensitive. I would love to have had the data from those students. I don't have it. The fact that we can see differences in their reasoning, I think, is encouraging. These are good students. How do good students get to be good students? Well, they're fairly teacher-proof. They're fairly method-proof, okay? So they like it, and they do well no matter what you give them. So they're not the best, they're not the most sensitive instrument for seeing these differences. I think it is worth exploring. So there's a flaw with the sample, I think, in that study. I think there's also, we don't know then if the test itself is sensitive to the kinds of differences that are important. So we were also a little surprised that we didn't get a stronger signal out of that test, but it was a test that's where that study, the bulk of that data was collected, was in these presentation-focused courses. I would also add that collaboration, when I talk about collaboration, I don't only mean structured small group work. Students talk very articulately about collaborating with the class. I have worked on my own, and I contribute to the class. We as a class solve this problem. So I think even in a presentation-focused course, which tends to be the upper level courses, right? You tend to do this for the math majors. You don't tend to do this with the pre-service teachers. They tend to be a little more skittish about getting up to the board, right? So the group work tends to be in lower level courses. It tends to be in different kinds of courses. In those presentation-focused courses, I think the important thing is that discussion does happen, right? And if it's all the dialogue is between the instructor and the student, that seems to be less powerful than the student puts something up and other people start chiming in and suddenly lots of people are participating. So I think the back and forth between student presentations and discussion is important. And I do think that is part of what students, I know that is part of what students are talking about when they talk about collaboration, right? They mean the work we do together in class. They also mean the work we do together out of class, right? Students form study groups. They talk to each other. They come to office hours and they work together. You've seen them in your offices doing this. So when I say collaboration, I don't mean only cooperative learning, structured small group work. I mean working together, co-labor, right? And the labor is important. I absolutely agree with you, right? Part of why this works is time on task. The tasks are motivating, they're challenging, and they want to put time into them. So that is absolutely part of it. But the interesting thing is, why are they willing to do that for this method, and they may not be so willing to do that for lecture-based courses? Okay, great, one more.
Given the dramatic improvement or increase that the statistics show with the low-achieving students, do you think it would be beneficial to actually have the IBL course be given for the trailer courses, what we used to refer to as the trailers? It was like Calc 1 being taken in the spring semester, which is largely populated by people who did not pass it the first time. So, rather than those people just taking the same course the same way again, probably many of them achieving the same results again and again and becoming disappointed, do you think that it would be beneficial to change those trailers to be IBL, and if so, how would you try to implement that?
I think that's an interesting idea. It could be very powerful. I think the tricky bit would be, do you have enough students willing to take a swing at this to make it fly? I mean, if you have a bunch of students who are reticent and not confident, that will be a challenging group to get moving, and you're going to need to be clever in your tactics. That said, there certainly are tactics you can use for those kinds of students and those kind of situations, but starting with them standing at the board the first day probably isn't one of them. So I think that's an interesting idea, and I think that'd be very worth paying attention to if you tried it. Pay attention to the DWF rate and things like that. DWF is not a meaningful measure for these upper level courses that are mostly, pretty advanced and skillful students. So, there are going to be different effects, and I think that's a very interesting research question to look at what happens in lower level courses and courses for students who don't come in with as much pre-existing interest in mathematics. Okay, great. Thank you so much.